Okay, can everybody hear me? If you can hear me online, type something into the chat, and Amin will tell me if it looks good. It's good? Okay. So, yeah, sorry for the delay. Slightly frazzled after driving in the overheating car. Um, Actually, engine was smoking when I took it into the garage downstairs. I let it cool off for a few hours before taking it a kilometer and a bit away. Uh, so, research survey paper. So this is what I was just asking about this, and conveniently I have a slide on it. So it's due December 20th. I'm pretty flexible on that. So the reality is I'm not going to be like December 21st. I'm just banging out, marking all of these things. So this is a good target for you, so you can just be done at the end of exams and enjoy your break. There's no reason you can't have it done by then. But if this causes you stress, you're like, look, I'm writing a test on the 19th. Can I have more time? Yes, you can have more time. I do need to get the grades in like by about January 10th or 11th, so you can't have infinite time. I experimentally have determined that missing that does get noticed. One year I missed, let me turn the projector on so you can see what I'm showing you actually, sorry. So that might be what you're saying, Alex, is I have no slide, thank you. Not trying to convince everybody they should be online. Yeah, one year I took so long getting the grades in that the chair of, the graduate chair within ECE stopped emailing me and started coming to my office and knocking on the door to like talk to me in person. So that convinced me I should never be that late again. So let's see, what is taking this? Okay, there. Should be able to see that. All right, I think I hit the last button. Okay, so it's due December 20th, but if that causes you stress, send me an email. I'm going to be pretty flexible on it, but I guess what I'm telling you is once we get, you got to get it in December because I got to get the grades in early January. It's worth 25% of your final mark. So these are guidelines to give you some ideas, some structure. So typically you want to read 8 to 10 papers in some area that interests you. There are a whole bunch of ideas in the assignment. You're not limited to that. If there's something else you're interested in, you can go ahead and write a paper on it. If you're not sure, you can ask me about it. Often students will line this up with, obviously their interests, but also maybe what they want to do for their graduate degree. So that could be a good way to start your prior work. Usually 8 to 10 papers is too much to summarize in detail. So you read them, you should reference them, maybe you put them in a table, maybe you quickly overview them. But dive into some limited number, maybe the most interesting or contrasting 2 to 4 from that, you dive into more. I want your thoughts, okay? So I don't want, here are 3 abstracts that I've reproduced plus a whole bunch of figures. Tell me what you think. So what's the same, what's different, what should be future work? Which, is the kind of the hard part. How would you organize these things as some kind of coherent whole? Target is 2,000 to 3,000 words. There's a penalty for over 3,000. Almost nobody goes over 3,000. That's why in the document it says like count how many words you're over 3,000 and calculate the penalty. That's intended to make you go, I'm going to stop writing now, right? Because I'm not going to keep writing to make my grade go lower and lower. You should include figures and tables. They don't count in your word count. 2,500 words of text on a research topic with no pictures and no tables is difficult to read. You can reproduce figures or tables from some of the papers that you read. If you directly reproduce a figure or a table, you put a reference in the figure caption, okay? That says, I took this directly from this paper. It's fine. You could also draw your own, right? So you're probably not going to draw a whole lot of figures, except maybe an overview figure. You might come up, sometimes you come up with, here's a table that actually contrasts all these papers on a few axes. And I made my own table, and that can be very interesting. But maybe you don't think of such a thing. Maybe you just reproduce key result tables. Don't start reproducing like here's 40 figures and tables from these papers because it won't be very comprehensible, right? You have to be judicious of what do you want to put in that kind of makes your point without overwhelming me. You're writing it in LaTeX like you did for the other assignments, which is a good experience for, this is probably the best way to write research papers, so it's helpful for your research. And that's it. Any questions on that? Yeah. General flow. So I guess I'm giving you an idea of this. You can actually look up survey papers and see. So you have an introduction. You can write an abstract, but you don't have to, okay? Because on a paper like this, you don't really need to write an abstract. If you feel like it, you can. So you have an introduction that lays out what is this area about? Like, why is it important and what is it covering? And often in that introduction, you might briefly list is like 8 to 10 papers, like you cite each of them, saying a little bit about them or how there's a lot of research that covers these various axes. And then you're trying to get into your deep dives. You're saying, well, there are two fundamentally different approaches that I see. One exemplified by this, one exemplified by that, and I'm now going to dive into each of those. And maybe you have this next section is all about one of those approaches, the section after is about the other approach, and you might have like an analysis section after that where you say, well, let's contrast these a little more, and say what you think should be done that maybe nobody's doing. And then you might have a final conclusion that's quite short because the way I just described that, most of your analysis has already happened. So that's one way you could do it. It's not the only way you could do it. Does that make sense? But I am looking for, an intro that lays out the landscape, information on these papers that includes contrasts. So maybe that's integrated as you're talking about the papers, you're contrasting them. Maybe you tell me about them and then you do the contrasts afterwards. Doesn't just have to be contrasts. It can also be similarities, future work, but bring some of that. Does that make sense? I'm digressing a lot today. I think it's because I was freaked out by my car overheating. Okay, so there's a master's thesis where the student had cited a survey paper on deep learning on FPGAs. And I hadn't seen this survey paper, so I went and looked it up. And it was amazingly bad, okay? And I had never heard of the person who had written this survey paper, which is odd because I work on both deep learning and FPGAs. So this is odd, this person's written this survey paper, I don't know who they are. And then I told this to one of my grad students, Andrew Boutros. So he looked the guy up, and he goes, this guy has written like 20 or 30 survey papers on everything, survey papers that are all sorts of different topics. And he even has a YouTube video on how to write a survey paper. And his method for writing a survey paper, which you should not follow, do not go watch his YouTube video, is basically find a hot topic. That's why he has survey papers on all sorts of things. It's not be an expert. It's like find a hot topic. Go read, not 8 to 10, he says read 70 to 100 papers on it. You don't really have to read them carefully though. What you do is you're going to cite 70 to 100 papers. You're going to take like kind of key points from their abstract, write them in. You should make a table that contrasts them. And he gives examples of that, and like it's all like sort of mechanical, right? Like the contrast is, you don't really understand much about what's in these papers, but you just kind of look through and go, how could I categorize them? Like big versus small, fast versus slow, things that anybody could do. And then you conclude your survey paper. So don't do that, okay? It was kind of amazing actually, because he has written survey papers on all sorts of things, and he has a method of just like find a hot topic, write the first survey paper on it, and some people will cite it because they're just looking for a survey paper. So, I got the student to change which survey paper she cited. So, yeah. Yeah, you should write it in LaTeX, just so it looks nice, and it's good to learn how to use LaTeX. If you make it look like LaTeX, and it's not, I guess I can't really tell. But I would say, so you get it in a nice 2-column format that we've given you. Okay, we can't tell. It's probably harder to do that than it is to learn basic LaTeX. So I had one paper years ago, back when I wrote some papers in Word, where I wanted a certain figure to go in a certain spot, and I just gave up. After 2 hours of trying to make Word move it there, I just decided that having it in a different spot was okay. Okay, the good thing about LaTeX, it doesn't have it. Once you figure it out, you can control everything. Okay, last week's reading. So 2 papers. How many people read the first paper? Okay, how many people read the second paper? Okay, so paper reading is getting low. I posted them late, so you've got a few more days still. And as I said, this paper is very dense, but I think it's a great paper. If you read it and you understand what they're talking about, you know a lot about where FPGAs are headed. Yeah? Oh yeah? So you found it very dense? Is it too dense?
I didn't write the file. I would equate it to like a 15 to 20 page paper instead of a 10-page paper.
Huh, okay. All right, you may not be selling it. Did you enjoy reading it or not?
Yeah.
Or you were like, oh, that's like 7 hours I'm never getting back. So, yeah.
I didn't like the intro too much, but I definitely found the body nice.
Okay.
It made some good points.
What do you think, Isidore? Did you like it or not?
Well, I didn't write the reply on it.
Because it's too complicated? Really?
Had a long week.
Okay. Well, you still have some time if you want to. Okay, that's interesting. I'll talk to you guys afterwards to see if it's like one I should keep for future years or not. How about the second paper? How many people read this one? Okay. Okay, so paper reading has fallen down. But what did you think of this one, Alex?
This one was actually, well, I actually really liked it.
Yeah, it's a very, this one, it's kind of almost opposite. The second paper is kind of, it's checking one thing and it does it in a very understandable way. So, so you still have a few days, and if you're going, okay, I want one that's like not too hard to read, this one is going to be easier to read. But they're both good papers. Okay, for next week, two architecture papers for recent FPGAs from Intel. So one on Stratix 10, one on Agilex. We'll talk, one of the big things about Stratix 10 is it puts registers right in the routing. Agilex then tweaks that. So we'll talk about both these probably next week, maybe in a week and maybe 2 weeks. So we'll see when we get to it. We're not only going to do, we're also going to do a couple of, well, one or two recent architecture papers from AMD as well. But these two just kind of fit together nicely. So we'll read, AMD actually has some nice papers on Versal, which are coming soon. What's that? Yeah, Jeff Komchek is a good guy. So, okay, course concept map. So where are we right now? So we're looking at the details of FPGA architecture. We've looked at logic blocks. We've looked at arithmetic and RAM. We're looking at other function blocks and moving into routing. Okay, so hard blocks. So I talked at the end of last lecture about, how do you evaluate if you harden something or not, and that power concerns push you to harden more things. So that's kind of interesting. Let me turn this on, it might be better. Okay, so another major hard block that basically every modern FPGA has is DSP blocks. So I told you that one of the things you want to look at when you're hardening a block is not just how much smaller does the function get, and how often people use it, but those are two things you want to look at. You also want to look at how it interfaces to the routing, because if it needs a lot of connections to the programmable routing, even if hardening it shrank the function of the block a lot, you can wind up with something that's pretty inefficient because the interface to the routing is so big. Okay, so let's look at a multiplier. So what I'm showing here is an array multiplier. So the basic way, there are a few different tweaks on multipliers, but they all have the same fundamental property that you're computing partial products. So you're ANDing bits. So I've got one operand coming in here, okay, and one operand coming in here. Maybe I'll do that maybe I'll do it up here. I've basically got my two operands, and the normal way you do it is you bring one in here, one in here, and every place where they cross, you have basically an AND gate. Okay, so you compute a partial product. You need a 1 in both multiple cans to get a 1, and then you're going to add all those bits up. Okay, so you've got a combination of a whole bunch of AND gates and a whole bunch of adders. And it's just like how you do multiplication with a pen and paper, but you're doing it in binary. It's the same procedure. What this means is that they get big. If you have an n by n bit multiply, you need n squared basic logic elements, right? You need n squared AND gates, and then you have to add those together, which is approximately n squared adders as well. Okay, and they're pretty common. People use multiplication a lot, so this was a good candidate to harden. So we should check, does it have too many inputs and outputs? Because if it is still not a good idea, well, it has, okay, if I'm multiplying two n-bit numbers, I just have 2 times n inputs, and then I get one output, but it's twice as wide, so I get 2n outputs. So that's good, because that's linear in the bit width, whereas the amount of compute is quadratic in the bit width. So especially if I've got large multipliers, this is not going to be bound by the routing. Like I'll get a good win here, even including the routing ports. Does that make sense, everybody? So that's the fundamental reason that FPGAs harden, well, all those are the main reasons that FPGAs harden multipliers. They've been doing that for years. Okay, so a lot of multipliers, I guess in wireless signal processing, which is, I guess in signal processing, well, for the wireless market, that's one of the biggest markets for FPGAs. It's been a big market for a long time. So the early DSP blocks were really architected for that market, right? Signal processing for communications. And you could use that for some other things, but communications was the key thing. And it turns out that 18 bits is pretty good for that, okay? It gives you enough signal to noise ratio. So more than that, you usually don't need, it will waste area. Less than that, and it might not give you enough precision. So let's say I've made my architecture and I've decided to make an 18 by 18 multiplier. This is what I was talking about. You've got two inputs. Here's one input, here's the other input, and I basically have this array of AND gates, and I'm going to add them all up. And it gets shifted over one for every bit position because the significance of the partial products is increasing as I basically go down, this input. Again, it's exactly how you do multiplication with a pen and paper. So if you don't remember that, you have to multiply some numbers by hand for a while. Okay, so in an FPGA, you'd ideally like to use things, you want to make things as reusable as possible, right? We're trying to make a very generic device. So can I, without adding much circuitry, could I make this more usable? In other words, make it do other things besides an 18 by 18 multiply. So what do you think? Alex, what do you think you could do?
Because instead of an 18 by 18 multiply, you can turn it into two 9 by 9 multipliers.
Okay, how would you do that?
You have to kind of store the partial products in the middle.
Right. So you basically, what's actually happening here is I'm computing partial products. I got all sorts of AND gates, and then I basically have adders. So there's carries rippling across this boundary. I need to break those carries. But that's not hard. That's basically another AND gate. So put a little bit more circuitry in, and I can stop these carries from propagating across that boundary, and I can control that with an SRAM bit. So sometimes they propagate, sometimes they don't. And yeah, that would make two 9 by 9. It looks like I can make 4. Okay, so I can actually also, there also are sums that are basically propagating this way. And if I put to use the same trick, I put a bunch of AND gates on my second red line. I stop those AND gates from propagating if, again, I'll need like an SRAM bit. But I take an SRAM bit, the CAD tool programs 0 in, it'll stop those sum bits from propagating as well. So I've now divided this up into 4 9 by 9 multipliers, and I didn't add very much hardware. Okay, I haven't shown you the detailed hardware, but take my word for it, I can do it with basically an AND gate on each one of these dots on these lines, or equivalently a multiplexer. So it's not very big, just a 2-to-1 mux or AND gate. So what do you think? I've just made 4 9 by 9 multiplies. Sounds good. Alex was only looking for 2. I made 4. Sounds like I did well. What do you think, Isidore? Yeah, so from a logic perspective, 4 9 by 9 multiplies makes perfect sense here. But it doesn't work very well in terms of routing ports. I basically have enough routing ports. So I had enough routing ports for 2 18-bit multipliers, or multiplicans to come in. That's enough routing ports for 4 inputs that are 9 by 9. But 4 inputs only let me do 2 9 by 9 multiplications, right? Each multiplication needs 2 inputs to do something useful. So I have enough compute that I could have done 4 9-bit multiplications, but I only have enough routing ports to do 2. So, okay, I guess another question we should ask is, not useful? And yeah, it is useful. It's common in video. So it's, you think of pixels. Pixels are usually like 8-bit color for RGB. 9-bit allows me to have a little bit of sub-pixel precision, so it's not bad to have that extra bit. Machine learning, 9-bit is a very common precision for deep learning. You don't need, you just did this in assignment 2, and 8 bits is very realistic, right? You can push the precision down below 18 bits. So yeah, we can use this. It's cheap, but we can't get 4 9 by 9 multipliers out of it. We can only get 2. And so you'll see various FPGAs that do exactly this. They'll have a multiplier that can do 18 by 18, or it can be divided down to 2 9 by 9. The reason it's 2 9 by 9 instead of 4 is because of the input and output limitation. If you were just talking about compute, you'd get 4. Okay, and yeah, this happens all the time. You're limited by the inputs and outputs. So, okay, a few other things that, yeah. Supported 3 9x9s. Yeah, I think it did not 36 by 36, it did 27 by 27 for ARIA 10. So if I go back to older Intel Altera architectures, they could group together four 18 by 18s to do a 36 by 36 inside the DSP block. So you can do the same trick, but sort of in reverse, grabbing multiple 18-bit blocks with some dedicated connectivity and do a 36 by 36. So early Intel FPGAs with DSPs did that. Turns out 36 by 36, you don't really need that often. What is very useful, though, is 27 by 27. Why is 27 by 27 useful? Because single precision floating point, the mantissa is 24 bits, but you needed 3 extra bits for essentially guard bits to get the rounding correct. So if you do 27 by 27, it allows you to do floating point single precision more efficiently, because the multiply you have is now the size you need for the mantissa. You still need a bunch of soft logic for the exponent, like handling all the exponent and shifting, but that's the reason, unless you harden that too, which the most recent FPGAs have done as well. But basically 27 by 27 is a nice number for mostly single precision floating point. It can also give you somewhat more accurate signal processing, but key use case is it's part of floating point. Does that make sense? So that's the 27 by 27. If your fundamental reason you were building something was, yes, you're saying, why do I get 3 9 by 9s? I'd have to go look at exactly how many ports they built, but they actually can do multiply accumulate. So my guess is if you count up all the ports, that they built enough for the 27 by 27 mode in multiply accumulate and not quite enough for the 9 by 9. It's a bit of a wishy-washy answer, but I think that's why it's maybe only 3. Yeah. Right.
A0 times B1 is the second one. Why couldn't we do A0 times B0? Same number of routing ports, but I just kind of configured it with that.
Oh, so you're saying, could I do like A0 times B0 and also A0 times B1?
Exactly. Wouldn't that be helpful?
You could, but you can also do that with just by adding B0 and B1 outside and then multiplying them by A0. So you're right. You could say with some restrictions, I can reuse these ports in different ways. And that is done in some chips. So if you get into all the modes in DSP blocks, you'll often find there are complex number modes. If you look at multiplication of complex numbers, you'll see there's some reuse of the data. And so sometimes they will actually expose that mode because they can effectively get a little more done. But yeah, for this particular case, you're right. I can do A0 times both of these, but I can just equivalently add these two outside. And adders are pretty cheap. Does that make sense? Okay, so I told you that signal is an important thing in FPGAs. And one-dimensional convolution, a finite impulse response filter, is heavily used in communication signal processing. In a lot of cases, not all, but in a lot of cases, these filters are symmetric. Okay, so it's basically just a coefficient times delayed, various coefficients, n of them, times delayed versions of the input signal. So you got a stream of inputs, you're going to convolve them with a bunch of filter coefficients. That's what this is doing. Often the filters are symmetric, which means if you have n filter coefficients, it's like the first and the n minus 1 are the same, the second and the n minus 2 are the same, and so on. That has nice properties, so a lot of filters use those coefficients, but not all. When you have these symmetric FIR filters, you can basically refactor the computation to do you only have half as many unique coefficients, but each of those coefficients multiplies 2 samples, right? One very recent and one older. So you can basically do the trick that we were just talking about, add some of your inputs. So this is like the most recent input and one that was delayed quite a bit, and so on. And I can do half as many multiplications. Okay, so that's a common trick when you have symmetric FIR filters. So DSP blocks the first DSP blocks did multiplication, and they just called them multipliers. Then they added in accumulate units, so they can now do multiply accumulate. And then gradually they added in more hard circuitry for their key use cases. So a symmetric FIR filter, this is my stream of inputs, say coming from an antenna. So we call that X, and every one of these dark things is a register. So if it's a symmetric FIR filter, so remember that means that I've got not n coefficients, just n by 2, because pairs of them are the same. I basically am going to delay my input, and the reason I'm delaying my input is so that I can look at a whole sequence of numbers, right? That's what a FIR filter does, is I'm going to take that sequence of values and multiply each of them by a different coefficient. When it's symmetric, I can add pairs, and that's what I'm doing here. So this is basically making use of that transformation, if I can add pairs of samples and then multiply by the one coefficient. And this architecture is called a systolic array. So a systolic array means it's a very highly, I don't actually know what the exact definition is, but it basically is a very regular hardware structure where all the data moves essentially like a beat every cycle. So the systolic array, I have this data streaming in, my X data. I'm adding pairs of inputs, and then I'm sending them into a multiplier by the appropriate coefficient. And then I'm not actually adding them in a tree. That's one way I could do this, is I could take all those multipliers and add them in a tree afterwards. Instead, what I'm doing is I'm adding them in a linear chain, which mathematically is fine, right? Usually you wouldn't want to add them in a linear chain because it would be slower, but I put pipeline registers in between them all so that this linear chain is very fast, okay? And this has very local routing. So it can be clocked very quickly. And the most recent DSP blocks from FPGA vendors can basically put this whole thing in a DSP block, okay? So all of this is, the multiplier is the biggest single thing here, but they also harden this adder, they harden the registers around it, they harden this adder in front of it, so that if you have a symmetric FIR filter, you can add these coefficients in hard logic, or add these input samples in hard logic. And they actually use dedicated routing for this, much like a carry chain. So this is usually done with what the DSP block calls a DSP cascade that only goes from one DSP block to the one right above or below it. So this makes them really good at FIR filtering. And an assignment, well, at least one person actually used all this hardware in assignment 2, because this is a one-dimensional convolution, but you can use this as one dimension of your two-dimensional convolution too. And this is about the most efficient way you can do convolution in an FPGA. Okay, so this is from that Principles in Practice survey paper. This is basically how much did we gain by doing this, okay? So this, again, took data from Stratix 4, where the reason to do Stratix 4 is the areas of the blocks are known. So we can actually do a rigorous comparison of how efficient is soft logic versus this hardened structure. Okay, so this is being done for 2 cases. So a symmetric filter. And let's see, the symmetric filter, let's start here. Let's say I didn't have any DSP blocks. So I get a certain area, 3 millimeters, and a certain frequency, 220 megahertz. And that's if I want a very flexible FIR filter, where my coefficients are just in registers. I can change them at runtime. Now, sometimes I know my coefficients when I do the compile. If they're never going to change, then the CAD tool for the soft logic implementation can actually do more optimization. It can see which bits are 1, which bits are 0, and it doesn't actually have to build the whole multiplier. It can get rid of parts of it, because I know what's ANDed with 0, I know what's ANDed with 1. So if you do that, actually it got quite a bit smaller. Took about half the area, and it ran somewhat faster. Then the third case here is do it with DSPs. Okay, so if you do it with DSPs, it got 3 times smaller still, and its frequency was much higher, went all the way to 510 megahertz. So you get a pretty big gain here. So versus the more flexible FIR filter, we basically improved its area by 6x, and we improved its frequency about 2.5x. So pretty big gains, even including all the routing ports, by hardening this. In Stratix 4, it didn't actually have this adder hardened, okay? Which means when you use the DSP block for symmetric filters, you had to leave some of the logic, like that adder, in the soft logic. That's okay, it still works. But it means that the biggest gains happened when you couldn't do that trick, when you had to build all the multipliers, not n over 2, but n. Okay, and in that case, hardening, going from like the soft logic, and I can change the coefficients, to the hard DSP block, we actually got a gain of over 8x in terms of area, and now still about 2.5x in terms of delay. The next generation from both Intel and AMD basically put those adders in. Okay, so the DSP blocks have gradually, every time you kind of find, hey, people are doing this a lot, they do it enough, you think maybe I'll put that in my hard block. So DSP blocks have gradually gotten a bit bigger, but more capable. So in the next generation, the area improvements you'd see would be more like this, even for the symmetric case, because those adders moved inside the DSP block. So it's pretty big. But once you add in the routing, it's still not as big as that. Remember, we looked at that Quan and Rose paper that said the gain in terms of areas maybe like 30x, soft logic to ASIC gates. We never get a number that big, right? Our best number is like 8.5, because we have to add in the routing ports and all these other things. But it still could be a big gain. Let's see. Does that all make sense? Okay, so this is again from the Principles in Practice paper. It's a busy but beautiful, I believe, picture. You could print this out, hang it on your wall. Your significant other might be very impressed, saying, I was always looking for DSP block art, and thank you for finding it. So yeah, Xilinx was the first one to put hard multipliers in an FPGA. And then Altera put in essentially adders, multiply accumulate units, and then called it a DSP block, so it wasn't the same as what Xilinx called it, right? So they had multipliers, Altera said we have DSP blocks. And then there was gradually, they've gotten more and more powerful. So there's a sequence here of gradual improvements. A big one here was ARIA 10, so the chip that you used in assignment 2. And the big thing it did was put in floating point support. So until that point, FPGAs were always fixed point, and basically you should do the extra work to figure out how to make your algorithm accurate enough in fixed point. In ARIA 10, Intel decided we'll just make it possible to do floating point because we don't think we can convert everybody. And that did make it very desirable. Like, you naturally need a 27 by 27 multiplier to do that. You also need some extra logic to do shifting and keep track of the exponents. So they hardened all of that. And as part of the reason why you see it, some of these earlier ones did 36 by 36 multipliers. This one's now doing 27 by 27. It's because it lines up with floating point so well. Yeah. Yeah, so a good question is, how much bigger did this get? Because maybe this is a really bad idea. There's a paper on this, actually. It's an interesting paper. Martin Langhammer is the first author on it. It was only about 10%, okay? And he used all sorts of tricks to do that. So he did, I'll have to look it up, but it basically increased the area of the DSP block by about 10%. Part of the reason was they decided, okay, we're not going to do 36 by 36 anymore, we'll do 27 by 27. So one of their fixed point modes lines up perfectly now with what they need for mantises. And I forget all the other tricks, but they didn't add any routing ports. That was another key thing. They had enough routing ports to do the floating point 32. And then he was clever in all of the other parts in a way that I don't think I can actually describe. You have to read the paper and then maybe phone Martin. So there was much less than people had thought it would be needed. Like, straightforward implementations that didn't reuse a whole lot of logic would have actually been much larger. So one of the key enablers of this was a very clever implementation. And then basically, you know this is a good idea when it's adopted by AMD. And AMD chose to put in FP32 and actually went one better. There are now lower precision floating point formats, FP16, that are useful for machine learning. So they put that in, because by the time they did this, it was clear machine learning was becoming a bigger deal. And then the last one that I'm going to talk about is Stratix 10NX. So this is an architecture that is from Intel, and it focuses on machine learning. So it adds some more, all of these other modes were mostly for signal processing. The floating point was partly signal processing, partly high performance computing, people doing like radar processing and even physics equations. This chip basically took out, you notice that it doesn't actually have 27 by 27, it doesn't have 18 by 18. So it took out some of the modes that were needed for communication signal processing, and instead what it put in is a whole bunch of really small multipliers. So it can do 38 by 8 or 64 by 4 multipliers, and that's targeted at machine learning. A lot of machine learning is done at 8 by 8, some's done 8-bit precision, some is done in 4-bit. Yeah?
Was that architecture otherwise like Agilex, like with the 10?
Yeah, so this one was done before Agilex. So Stratix 10 is Intel's second most recent architecture. They took Stratix 10, they ripped out the DSP blocks, left everything else the same, and put in this new NX DSP block, something that they call the tensor block, because it's targeted at machine learning. And then you go, well, is that a good idea or not? Well, the next generation device from Intel is called Agilex, and it has put these modes in the DSP block, which means they at least think it's a good idea. Like, whenever something goes in one generation and comes out the next generation, it's kind of, okay, it didn't work out so well, right? But the fact that it went in the generation afterwards means that they think it's a good idea.
The plot says it's the other way around, though, because Agilex is more.
How did I do that? Huh. Okay, well, I guess the original, okay, actually, I think what I'm messing up is the original Agilex, I think, didn't do it, but now there's an Agilex NX. Okay, so the most recent Agilexes, which I think they called Agilex 7, have this in it. So I guess yeah, if I want to make this plot even more confusing, there's another Agilex after this that now has this in it. So, but that's a good question. Okay, so what are the trends? Somewhat more fracturability over time, like the early Xilinx DSP block could just do 18 by 18. And you can see you're getting more and more options in terms of what precisions you can do over time. You've gone from multiply to multiply accumulate to basically being good at dot products and FIR filters. You could do that before, but now you can bring the adders in and even pre-adders and everything you need for a FIR filter. And then floating point has come in. And then, yeah, I talked about Stratix 10 NX, which basically gives you a very large number of low precision multipliers. But the obvious problem with that is going to be, well, wait a sec, that sounds like a lot of inputs and a lot of outputs. So what's going to happen there? Because the logic in a multiplier is quadratic in the bit width, an 8-bit multiplier is not that big, and a 4-bit's really small. But this is a lot of inputs and a lot of outputs, so there is a problem here. Is that going to be your question? Yeah, so let's look at the tensor block, because it's interesting. So in the same area, so the paper that introduces this says they basically kept the area the same. They take out 2 18-bit multipliers and some floating point support and so on, and they're able to fit in 30 int 8 multipliers or 60 int 4. So they can fracture the int 8s so they can actually do either one, right? They basically built 30 int 8 multipliers, but each can be decomposed into 2 int 4s. So that's pretty good. They were able to fit this in. But then if you go and count the inputs, the DSP block that is in the regular Stratix 10 has 96 inputs and 72 outputs, okay? And those are expensive. So you don't want to increase that much. If you just take how many inputs do I have with 30 int 8 multipliers, well, it's 30 times 8 times 2, 480. And then the same thing on the outputs. I'm going to produce 16-bit outputs, and I'll produce 30 of them, so 480 outputs. Note that 480 is a lot bigger than either 96 or 72. So seems like this is a really bad idea. Like I've done something that's going to massively increase the size of this chip. So we can't, so what they did is they basically went, well, we're going to put restrictions on how you can use this. We can't just hook up that many inputs and outputs to the program we're running. It's going to be insane. Can't pay that kind of area. So the first thing they did is they said, well, we're not trying to do 30 independent int 8s. This is for convolution, matrix multiply. These are the like dot products. These are the key operations in deep learning. So what do all those things have in common? They're basically built around dot products, which means you don't need to have 30 independent outputs. You could add up a bunch of your multiplications, and that's okay. So they didn't add them all together. They thought that might be too restrictive. But what they did is they said, well, we'll group our 30 multipliers into groups of 10. So 3 groups of 10. Each of those is like a 10-element dot product. And the dot product doesn't produce 10 outputs. It produces 1 because you're adding them all together. So they now bring it down to 72 outputs because they only get 3 outputs. And let's see, let me see if I can do all the math here. 3 times 16 is, well, it's fine. Forget it. It's actually would be 48 outputs, but they brought a few other things out, okay? Because you go, wait a second, isn't that 48? It is 48, but there's a few other features in there. So they're fine with the outputs now, okay? And because they want to do bigger dot products, they also went, okay, well, we can cascade these summations across DSP blocks with dedicated routing. Dedicated routing is pretty cheap, right? It's just wires with very little, doesn't have big muxes. This allows them to basically make bigger dot products without any external adders because they're just going to have the prior block is going to feed in here and also get added in. So it's the same trick that I was showing you with that systolic fur filter. So I can now make 10-element, but even bigger ones with this cascade dot products, and I'm fine for outputs. But I've still got a problem for inputs. So let me pause there. Everybody with me on how they solve the output problem? Okay, so it sounds good. Okay, so they now need to limit the inputs. So 480 inputs is if I just bring in 60 independent 8-bit numbers. But they decided, well, we don't need that. We can live with less flexibility. So the first thing they did is they said, okay, let's take one set of inputs, and we're going to broadcast them to all 3 of these, okay? So they bring in a 10-element vector, and it has to be used 3 times. Okay, now this is a limitation, so they now can't do 3 independent dot products. One operand to these 3 dot products must be shared, must be the same vector. Okay, so that's going to be a restriction on how we use this thing, but it does cut your inputs from 480 to 320, which is still too much. So the second thing they did is they basically said, okay, we're also going to say the other 30 numbers, right, the 3 other 10-element vectors, we're going to basically preload those and use them over and over again. So they built in what are called ping pong registers, basically a form of double buffering. They can load one set of registers, essentially like a shift register, so they can load 30 numbers in here that feed into these dot products. And they can be loading that through a few routing ports while they're doing multiplications. And then when they have, so they've basically been using these other registers, this one bank of registers, they're doing a bunch of multiplications by numbers that they're broadcasting in. And after a while, when they've done all the dot products that should use these values, they, in the background, have been loading in new numbers in this other set of registers, and they just flip it. Okay, so this set of muxes lets them flip, if they wanted to every cycle, between the 2 banks of registers. Okay, so this is a pretty significant change in how you have to use this, right? You can't just write this in RTL and expect the tools to figure out what's going on. You have to organize your computation, that there is something you can broadcast, there is data you can shift in. You're going to multiply by a whole bunch of vectors to make, pay back how long it took you to shift it in. While you're doing that, you're shifting in more data. So you have to be thinking about how to use this thing kind of like a little compute unit, right? It can't just be you wrote a bunch of multiplies and adds in your RTL and said, Cordis, figure out what I mean. It won't, right? So, yeah. It only makes sense if you're actually going to multiply a bunch of things. Like you basically get these values in. Let's say these are activations in machine learning, okay? And then I have a whole bunch of different weights that need to multiply those activations to produce. So if you think of a CNN, I have a whole bunch of different output channels, for example, that are a function of the same input activations but use different weights. I bring in those input activations, store them here, send through all sorts of different weights, adding up various output channel values, storing them in some blockrams, and then I put in some more activations and keep going. Okay, so it isn't useful, like you need structures like that. If you didn't have a structure where I need to do dot products against this set of vectors over and over again, then it wouldn't be useful. Because you're right, you just spend all your time waiting to load, and there's no real purpose to have more multipliers.
So if this was a CNN, you would like load in one of the channels, and then while that channel is loaded in, you would now load in, let's say, the entire 512 by 512 image on that channel, or if it's the row, the entire row through that channel. And while you're putting all of the pixel values through, at the same time, you're loading the next filter.
Yeah, that's the basic idea. I can't tell you, like there are many ways you can do it. The basic idea of like a CNN is a good one because there's a lot of reuse of your activations, also quite a bit of reuse of your weights. So you can either kind of cache your weights or cache your activations, and you can choose to do it in different ways. But what you just described would be one reasonable way to do it.
Where something like a linear layer is not going to help you with structure.
Yeah, if there's no reuse, it's not going to help you much, right? Because you basically need the reuse or you're going to be limited. Does that make sense? Yeah.
I guess I have a bit more of a nuanced question. So one of the main things about the DSP block is that anyone who's writing anything on FPGA, the packer will handle, even if you're not a genius, the packer will handle making DSP block where you can put the
Yeah.
Isn't there something to be said that you're killing a lot of your use cases and clients from not being able to, like you have to be like some kind of mega genius to know everything about the architecture to be able to use this?
Is this fundamentally harder to use? So I agree. Like one of the things when you're making compute accelerators is what is your programming model?
Yeah.
Because there are lots of people who made compute accelerators with no programming model. And there are only actually a few successful programming models. Like CPU is essentially its programming model is like sequential C with a few add-ons. GPU, which is basically SIMD. FPGA, which is RTL. And actually not a lot of other ones. So you're right. So you go, well, wait a sec. This doesn't, the way you would use this is you instantiate it in your RTL, but you have to do all sorts of data movement around it. So it is harder to use. You can't just write vanilla RTL. So it's a good question. It does get more performance, but it's kind of changing your programming model when you want to get the most out of it. One thing that may help in this case is if you're targeting machine learning, you can wrap it in an API. Okay, so lots of people, frankly, I mean, this is NVIDIA's big barrier to entry. Their hardware is very good, but their big barrier to entry is their huge software stack, where the vast majority of people using NVIDIA GPUs to train a machine learning model have absolutely no idea how they would make a performant machine learning model on NVIDIA, on a NVIDIA GPU, but they do know how to like just ask PyTorch to do it. So that's one of the things that can help. If you've got some experts that can map key machine learning kernels onto this structure, then other people can use that as IP cores, like potentially big IP cores, not instantiating just NX blocks, but like a big thing, like I want to instantiate a convolutional layer. And now maybe I don't know exactly what's going on in there, but somebody who was really good wrote it. Yeah.
With this kind of stuff, this only goes in like the machine learning NX version, the basic, Agilex or whatever follows it. It's not going to have it.
So for Stratix 10, this only went in this machine learning variant. For the original Agilex, it wasn't there, as you noted and corrected me. I believe for Agilex 7, it's in all the DSP blocks, okay? Which is a sign that Intel thinks this is pretty powerful. What they did for Agilex 7, sort of like almost a half step in Agilex, is they put this in, but they also kept the other modes. So Stratix 10NX kind of took out a bunch of the other modes and put this in. Agilex 7 says, okay, we need both, because we're not abandoning the signal processing market, and we've decided that we'll just make a unified family again. So we're just going to make these features plus those other features. The DSP block will be somewhat bigger, but everybody can use it again.
How much, like on the order of how much bigger would you say that would tend to be? Just because like.
Yeah, I'm not 100% sure. Yeah.
Area of the multiply, right? So this is
Well, there's a lot of area for routing ports too. So you do get to reuse the routing ports. You can do some tricky things where you try to like take your big multipliers and reuse some of the arrays or combine your little arrays into bigger multipliers. So I can't give you a very good answer. I think in order to put them together like that, they probably kept it to, like 20% would be probably a reasonable cost for them to pay. If it was 100%, they wouldn't pay that. Does that make sense? Or I think it's unlikely they would pay that. Okay, so what did they achieve? So this has 15 times as much integer multiplication bandwidth as the regular DSP block for int 8, 30 times for int 4, but with lots of constraints on how you can use it. So that's what they achieved with this. So I'm going to show you, like, actually I'm not going to show it to you. I'm just going to quote it. Sorry, for in the interest of time. I have lots more slides on this. So you guys already flagged this. It's not trivial to use a block like this. You can't just recompile your RTL or your HLS code and have it work. You had to actually restructure your computation. My group has done this for 2 different accelerators. We did it for HPipe, which I talked about earlier in the course. Remember, that's a CNN accelerator. It's what's called a data flow style. It means it makes a different processing element for every layer and hooks them together in a pipeline, so it's streaming hardware. So we actually looked at what's the best way to use this, and it was the best way. You can kind of structure your computation in different ways. What we found worked best was preload the activations and then broadcast the weights. And it's basically, we have many output channels that all depend on the same activations. So load those in, broadcast different weights, and we're gradually constructing different output channels. For dense CNNs are kind of the regular ones where you have all the weights are non-zero, or even if they are 0, you just do the multiplication anyway. We got a 5x speed up. Now 5x is not 15, okay? If we got perfect throughput from this, we would have gotten 15x. We do lose efficiency for a variety of reasons because we have to restructure the computation. One basic reason would be these dot product units are 10 elements long. If you have a CNN that actually has 32 layers, 32 is not divisible by 10, right? So you're going to do 10, 10, 10, and 2. So there are reasons why you won't be able to get perfect performance out of this, but we got 5x. HPipe, if you remember from a few lectures ago, one of the things it can do is it can also skip over 0 weights, which reduces the number of multiplies it has to do if you tried to train your network to have a lot of 0 weights, and you can do that. For those ones, because the computation is more irregular, it conflicts somewhat with this requirement to load things in, use them over and over again. We could still get some gains, but it was 1.9x. So these are quite significant because they didn't actually, in this case, they fit it in the area of a regular DSP block. If you want to read about it, you can go read about that. The other architecture we did is the one another one I talked about earlier in the course, the neural processing unit. This one is not for CNNs, it's for sequence models, things like LSTM, like long short-term memory. And its style is an overlay style. Okay, so remember, it's building big processing elements, kind of a very weird processor. It's got a matrix vector unit, it's got a bunch of SIMD, but it's controlled by software instructions. We found this also worked well. Again, it was best to preload the activations and broadcast the weights. In order for this to work, we had to batch. So GPUs have to batch a lot, right? In order to not process just, say, one image or one piece of speech. Because they spend so much time loading weights, they work best when you are saying, I've got a whole bunch of inputs and I'm going to reuse my weights. And FPGAs have been good at low latency inference because they don't have to batch. In order to make use of this, because of the fact that we're broadcasting our weights basically to 3 dot product units, we needed to use a batch of 3 inputs. So we needed to use a small batch size, but it was no longer 1. And then we got a good speed up, 3.5 times faster. So you can read lots more about that if you want. So I guess the takeaway from this is, yeah, it's a lot of restructuring. These were not trivial things to do. Like, this were months and months of work. But after doing that, you could get a good payoff. Not 15x, it's kind of Amdahl's law, but still enough to be quite significant when the block itself is about the same size as a DSP block. Okay, so that's all I had to say on DSP blocks. Any questions on that or tensor blocks? Yeah, and if this piques your interest, go read those papers. There's like tons of diagrams in there that I can't go through of how exactly you map this. Yeah.
Customers are willing to put in the months of effort to get these speedups?
That's a good question. So that's a question for Intel marketing, and maybe you could ask that of the CEO on the next earnings call. So I don't have the answer to that. That's one of your questions, right? And it's probably a question for everybody competing in machine learning. Well, okay, so they will put that effort in when they've got other stuff that needs to go in the FPGA, okay? Let me rephrase that. There's 2 different competitors here. One competitor is I'm putting it in an FPGA anyway, and my competitor is just a traditional DSP block that was easier to map to. So if that was good enough, machine learning was a small part of my application, then I might just go, it's not worth the effort, okay? If machine learning is a bigger part of my application, then it probably is worth the effort. And if it's a bigger part of my application but not all of it, then that I may need to be in an FPGA because I need low latency, I/O, talk to custom sensors, etc. There's another question of, well, what if I'm doing very standard machine learning in a data center? Now I'm competing against a GPU. In that case, the GPU just starts, especially an NVIDIA GPU, just starts with a huge advantage of this great software stack. So I think for that case, probably not. They're probably, especially for training, they're going to go with the GPU. For the case where it's a part of your system, you're already FPGA. If it's a big part of your system, you probably want to get this. They also want to get it, though, through IP cores, compilers, etc. So let's say you're doing CNNs. The output of this paper is not actually a piece of hardware. It's a domain-specific compiler. So if you want to use this on some different CNN, it will generate the hardware for you. And that's actually what they'd really like. So this one, you send in a TensorFlow graph, it makes the hardware. This NPU, you grab the NPU, and if you want to do a different workload that it supports, right, so it doesn't support every workload, it's a software compile. So that's what they really want. Give me an accelerator or an IP core. You can think of these as like super IP cores. And Intel's interested in that too. So they are interested in how can they enhance this, how can they make this available to their customers. And I'm sure they have internal efforts like that as well. Does that make sense? But your challenge as a company is you can never do everything for everyone, right? So that's why NVIDIA has this software stack is a big advantage. It's not easy to replicate it, like its breadth. It covers a lot of things. Okay, so second hard block example, which would be shorter, PCIe. So we talked about RAM blocks, DSP blocks. Those ones are, you make thousands of them. They're like really common. PCIe is a bit different. You're going to make only a few hard blocks for something like PCIe because you only need a few of these interfaces. But each one's pretty big. Okay, so let's talk a little bit about PCIe and serial transceivers. So I told you earlier in the course about a design example of DDR. So DDR is probably the most important example of what's called the source synchronous interface, where you send a bunch of data with a clock or a strobe that allows you to capture the data. Okay, so you align the edges of your strobe, or you align with the middle of your data window. So that's one way you send data at high speed. The other way you send data at high speed is with serial I/O. And generally, you do that when you're going over longer distances, where no matter what you do, your strobe and your data are going to get out of sync. And so you want to have really high bandwidth over somewhat longer distances. The coding, like the turning your parallel bus of ones and zeros into serial data actually takes a little bit longer. So the latency of this is a bit higher, but its bandwidth over long interconnects is higher. Okay, so for things like PCI Express, Ethernet, you use these serial protocols. Ethernet's a different one, but for 1,000 feet, it's a similar idea to PCI Express. Okay, so what does an FPGA do for these high-speed serial I/Os? So they break it into blocks. So the first block, called PMA, which I think is physical media attachment, is basically analog. And there's only a little bit of analog because you mostly try to do the very highest speed stuff at the very start you do with analog, and then you get digital as soon as you can because analog's hard. So here's my data. Okay, so I've got some received data here, and it's differential. At these speeds, you use a positive and negative I/O because it's more resistant to noise, basically. So we bring that in, and it goes into a differential amplifier, so it turns into ones and zeros. And the first thing we do is we have a clock recovery unit. Okay, so remember in DDR, we were sending a strobe for every 8 bits of data. So we sent the clock with the data. Here, we don't send a clock. We just recover it from the data. What that means is PCI Express and all other protocols like this have to guarantee there's a certain number of transitions in the data. You can't just send 0 forever and just go, it's just a 0, it never changes, because the clock recovery unit looks for edges. And the protocols guarantee you will get an edge every once in a while. And they use that to basically generate a clock. That provides control signals into a phase lock loop which is a clock generator. And now you basically recover a clock that's at the right frequency and is aligned with the center of your data window, okay? So it's actually kind of cool, very tricky. These are hard to design. This is like one of the highest stress jobs in, I think, many companies, like exact FPGA companies for sure. Often the leader of the team of the transceivers would only last 1 to 2 generations because it's just so, I mean, they didn't die, but they just like, maybe that sounds too harsh, but they like kind of did 1 or 2 generations. It's so stressful to make it work that after that, they're like, I'm going to work on something else, like inside the same company usually, but I am no longer in charge of transceivers. So, because these are made to go really fast. So, so 8 gigahertz, 16 gigahertz, now 32 and 64 gigahertz. So they go really, really fast. Okay, so the clock recovery unit, basically now I can sample my data. So I sample my data, I get a really fast serial bit stream. So for PCI Express, I'm going to talk about PCI Express Gen 3. That bit stream is 8 gigahertz, okay? I can't send that into my FPGA fabric. You're not going to close timing at 8 gigahertz. So there's a bunch of digital logic that basically implements the low levels of the protocol. This is all hardened as well. And these transceivers are used not just for PCI Express, they're also used for Ethernet and interlock and in various other standards. So we have a bunch of multiplexing that allows us to skip over some of these blocks because we actually want to reuse them for different protocols. Okay, so some configurability in it, even though it's hard logic. I'm not going to talk about most of this. One of the ones that's interesting, this is an 8-bit, 10-bit decoder. So I told you that you can't just send a whole pile of zeros forever because you can't recover a clock. You need edges. So one of the ways that you can do that is, let's say I'm going to send 8 data. I actually map that to a 10-bit code. And I only need 256 codes, and I have 1,024. The only codes I use have lots of transitions. Okay, so that is the way that the earlier versions of PCI Express actually guaranteed the transitions. Now, that means that I actually lost, I'm wasting 20% of my bandwidth. So later versions, more recent generations of PCI Express have switched to 64/66-bit coding and so on. So the fundamental thing is I need to get some transitions, but if I use a more complicated code, I don't have to sort of devote so many bits to it. Does that make sense?
Quick question with the speed you mentioned. You were talking about like 10 gigahertz or something. Is maybe I'm wrong. Is my understanding that like 10 gigahertz Ethernet is not actually running at 10 gigahertz. It's running lower, but it's got wider data to make it actually.
Yeah, that's true. Yeah, so the transceiver numbers I told you are like the raw transceiver speeds. So for PCI Express, I have to look at it. I think it's at 8.5 gigahertz, I think is the transceiver speeds for Gen 3. Gen 4, I think it's 16. Gen 5 is 32. So transceiver speeds keep going up. For 100 gigabit Ethernet, I'd have to look up what speed the transceivers run at, but you're right. They actually don't send just one lane of data. They send multiple lanes of data. But the transceiver speeds keep going up. Okay, so to go to 100 gigabit Ethernet, for example, they'll add more lanes, but they'll also run the transceivers faster. And I think they even have like multiple variations of it, so you can even choose like how fast are the transceivers versus how wide the lanes are. But basically, all these protocols want to send more data over the same number of links, so there's a lot of pressure to keep making the transceivers faster. So it's one of the value adds when you buy an FPGA. You're buying high-end IOs. They're actually really hard to make. Does that make sense? Okay, so this is all digital, and this is basically doing a bunch of low-level protocol handling. And then there's PCI Express that is common enough. There's actually a block to do some of the higher-level protocol of PCI Express, so like the transaction layer and so on. And then after that, we go to the FPGA logic. And the data stream's been widened a bunch. Okay, so we're not going to try to run it at 8 gigahertz. We've demultiplexed. We've done a serial to parallel conversion to bring this down to a wider bus with a much more reasonable frequency. Okay, I'm not going to talk about this, but basically the output path is just the reverse of that. But you can see there are all these muxes that the CAD tool programs in SRAM cells to say use this mux or don't use this mux. So you can skip over all sorts of parts of this protocol. So I can take these same transceivers and use them for Ethernet instead of PCI Express. Okay, so this is the same thing. The question, should I build a hardened PCI Express? So if I go back, so all the FPGAs you're going to buy now do have hardened PCI Express. So you should know the answer to this. The answer is yes, you should do it. But it wasn't always that way. PCI Express, for several generations, FPGAs did it with just, they needed some hard logic. Like you really can't get away from like this piece, okay? Like you need that high-speed analog. You need the first few bits of digital to bring it down to a wide parallel bus. So you can't avoid that. But the later parts of this, you can do soft. So if you build it soft, it's actually reasonably big. Tens of thousands of LUTs and flip-flops to build the protocol. If you put it in standard cells, remember the Kwan and Rose paper said it's 35 times smaller. We tried it. It was actually about 20 times smaller, so not wildly different. But for some of the reasons I talked about when we studied their paper, even for random logic, they're a bit optimistic, but that's still a big number. Hard logic's actually faster. Why does that matter? It matters because we're bringing in data for PCIe Gen 3 at 8.5 gigahertz. We make our data path as wide as we have to. Like even in ASIC logic, you can't run at 8.5 gigahertz. So we're fairly rapidly dropping that clock frequency and widening the data bus. If the logic runs faster, we don't have to widen the data bus as much. So that's essentially another area gain. The protocol is widely used. It's a standard, so you kind of know what to build. So that's good. We don't gain as much as you might hope because there are a bunch of variations, right? Gen 1, Gen 2, Gen 3, now Gen 4, Gen 5. You have to build, well, in this particular chip that I was working on, we built Gen 3. Gen 4 and 5 didn't exist. So we didn't have to build those, but we had to build all of these, right? So you lose something by having to build more hard logic than any one person's ever going to use, an extra bucksing. But it's still a pretty good win. There's also an ease of use win. You know, once you harden the IP, you verify it. There's a big cost if you screwed it up, because you can't sell the chip. But assuming that you get it to work, now it works for everybody. And I worked in the Quartus compiler team and worked very hard to try to make our IP always work. And we did improve it. And then I came to U of T and went, this stuff's super hard to use. So there is a benefit to hard IP of like it just works, right? There's no, maybe the compiler made a little mistake and didn't close timing or something. Okay, so PCIe Gen 3. The other thing you have in PCIe is how many lanes. So let's say I'm doing by 8. By 8 means I don't have one differential pair, I have 8 of them. So I get 8 times the bandwidth. This would be a pretty common configuration, but an FPGA is programmable. You have a bunch of options. Okay, so I've got 8 lanes. Each of them is running at 8 gigabits per second, and they're full duplex, which means I can send data out and in. So I've got 8, if I take this 8 lanes times 8 gigahertz, I've got 8 gigabytes per second at the FPGA IOs. And the FPGA fabric, let's say I can close timing at 250 megahertz. I'm pretty confident I can pipeline enough for that. But that is not, how do I match these things, right? How do I connect to this PCIe Gen 3 interface that needs 8 gigabytes of data if I can only run at 250 megahertz? What do you do? Yeah, so you got to go parallel. So okay, so I just work out, well, how wide an interface do I need? If I divide 8 gigabytes by 250 megahertz, I need a 256-bit wide bus, and it's full duplex. So I need that for inputs, and I also need it for outputs. So I have to build that. That has to connect to my design, right? Whatever I'm trying to do, that's what I'm going to connect. Okay, now the average logic block for this architecture, we actually looked at this architecture, and it actually has 52 inputs to the logic block. But on average, it doesn't actually use all those. Typically, it uses about 30 inputs and 20 outputs, which is a lot different than 256 inputs and 256 outputs. So we don't want to create local routing hotspots. Okay, so remember this rule of our channel width is equal to the number of inputs to our block times the average distance they came from divided by 2 channels. So it's going to be really hard for us to build a routing channel that supports both this logic block that needs 30 inputs and this PCI Express block that needs 256. Does that make sense? So what we do instead is we need to spread this routing demand out. Okay, so what we'd like to do is make this block kind of, from a routing perspective, make it look like a lot of logic blocks. Try not to make it look different, just make it look like a lot of logic blocks. So we take this 256 inputs or outputs. I'm going to do the outputs here. So I take the 256 outputs, divide by, or 256 outputs that I had, and how many times bigger is that than the average logic block? Well, it's 13 times bigger. So if a logic block hooks up to just, you know, say one vertical channel and one horizontal channel beside it, this should hook up to 13 of those. And then it's not going to produce any more local routing stress than 13 logic blocks would. Okay, but this puts a limit on the perimeter of the block. So basically, even if the logic for PCI Express was really small, you know, would fit here, I should not hook it up just to, you know, this one channel that comes right by it. I need to like spread it out to connect to like 13 horizontal channels and connect to 13 different pieces of this vertical channel beside it. And now it doesn't really present a local routing hotspot. If your block's relatively big and PCI Express is relatively big, this is okay. If your block wasn't this big, then it's a problem, right? Like you could wind up with something that's pretty empty because you just need to make a big perimeter to get enough, basically spread out your routing ports enough that you can connect to enough routing channels. Yeah?
Do you have to, it doesn't, the way you've drawn it, you're connecting it only to like the outermost edge of the LUT. But couldn't you instead say, you know, we're going to designate, let's say it's going to be half as tall, or we're going to designate twice as deep?
Oh, so you're saying like kind of reach into the fabric here
Yeah.
and say connect to another vertical channel here?
Yeah.
You could do that. It's problematic. I mean, there's a few reasons it's problematic. First, the horizontal channels are actually going to do most of the work here. The reason the horizontal channels are going to do most of the work is I'm hooking into 13 different horizontal channels. I'll get something out of the vertical channel, but some of these wires are longer, right? I've shown them all as length 1 here, but some of them are actually somewhat longer than that. So I'm going to wind up kind of connecting to some of the same wires. So I'll get benefit from the vertical channel, but not as much. If I extend my reach into the horizontal channel, it does help. But because of the fact that, like I say, I made this half as high, but I could connect twice in here and here, it does help, but there'll be some competition between those wires because some of them are longer. So it won't give me maybe twice as much, but it would help. The other thing that, and you can do this, right? There are ways to do this, and it is done in some FPGAs. In Altera, we call this a double driver region. We didn't really reach further. Just what we did is essentially create more endpoints of wires. So you can do that. Reaching further in could be a layout nightmare because this is typically full custom layout of all these logic blocks and routing wires. So it was very expensive. You replicate it over and over again. So hooking up to it at the edge, it's kind of unique, but it's okay. You don't want to do anything that's going to sort of disrupt it. But if you're interested, I can show you what a double driver region is. It's kind of a way to do what you're saying without completely disrupting the layout. You effectively consider this block, if you have length 4 wires, it's like you consider this block to be like twice as wide as everything else. So it's kind of, instead of 1/4 of your wires ending here, half your wires would end here. And you can do that in a way where it doesn't totally destroy your layout and gets a lot of what you said. Yeah, so that puts so that's another constraint you have when you want to harden these big blocks. These ones tend to be more like accelerators, I/O blocks, etc. So the DSP and RAM blocks are really kind of integrated in the fabric. They're very common. You want them to be not too different than the logic blocks. You don't need 1,000 PCI Express blocks, right? You don't have enough I/Os for it, so they're going to fundamentally, they can be more big accelerator blocks. You can afford to stretch them out and say they connect to a lot of different channels. Okay, that's it for function blocks. We'll talk about routing blocks after we have a break for, I don't know, till 5:37. Okay, I'm going to reclaim a couple minutes. Okay, so two. So that means we'll finish enforce all rules. So we have Isidore Kaplan, both much better than the GP, one of the cockles of my heart. Higher, two in the class, they hit megahertz, 142 megahertz. Tricks like using the fact that the filter's symmetric to do that pre-adder trick and to get rid of half the adders. Use RAMs for buffering, so the first thing you run out of DSPs, so very good throughput. Alex is in position 1 plus I. Okay, why 1? He achieved huge DSPs. The highest throughput was ALMs, so we made another version where he did soft multiplies to get 12,000 gigaops. He's just playing on a different mathematical system, right? So that's why I gave him, I thought maybe he's like position I, so he's 1 in imaginary space, but I just had 1 plus I. And then the top finishers were Herhan Zhu, Sohail Sharuz, and Hong Yan, who all three-way tie, because they basically hit the maximum of the DSP block clock frequency, and then they all maxed out the device basically. So they used that trick of symmetry to reduce the DSPs in half, converting multiplications to adds. Block RAMs in different ways, so they did it slightly differently, but they made sure the first thing they ran out of was DSP blocks because they were efficient in their flip-flops. Pipelined very deeply. Sohail used the cascade chains within the DSPs, so he actually built the systolic version that didn't even need soft adders. I believe the other two solutions used soft adders but very deeply pipelined them so that they could keep up with this. So well done, good throughputs. I promised Amazon gift cards. This is probably like the lowest wage you're ever going to get. So don't think of it as a symbol. Don't calculate your hourly wage because I'm pretty sure that it was not that great. Is Herhan Zhu here? Oh, okay. So, and if let me know if I'm mispronouncing your name. So
That should be good.
it's close enough. And Hong I know is on Zoom, but he's actually in China right now. So Hong, I'm going to send you an electronic Amazon card. So yeah.
Actually, something really interesting about my implementation is actually if you use no DSP implementation, you just use ALMs, you actually can get a higher throughput of like up to like 8,000 gigaops.
Oh, that's interesting.
So that's why
Part of that is maybe we should also change this so the filter coefficients have to go into registers.
yeah.
So you can still, for 8-bit multiplies, you can do a lot of them in the ALMs. So it's true, the logic fabric for small multiplies, you can do a lot. And it's about twice as efficient if you know the coefficients in advance, which with the code we gave you, a starter code, you know them in advance. So anyway, it is what it is. It has occurred to me that maybe we should make you load them into registers because then Cordis can't optimize them as well because it goes, I don't know what these are. Does that make sense?
I think even without that optimization, I was still able to get like an insane number, because it was the number of copies. The frequency was low.
Yeah. You can do a lot with soft ALMs. So it's true. If for 18-bit multiplies, you can do some. For 8, much better. For 4, even better still. So that's true. And there are papers actually on how do you make logic blocks more efficient for deep learning because of that. So for your research paper, if you want, you could go look into that. Anyway, so well done. And if you're going, wait a sec, I wanted to spend lots and lots of time to get a gift card, don't worry. You have another chance on assignment 3, right? So, but overall, there are lots of very good solutions, so it sounds great. Let's see, okay, so let me go back to where we were. And we're not going to cover all of routing architecture today, but we'll cover some of it. And let's see. Okay, yeah, Hong, you will get your card through the internet. Okay, so FPGA routing architecture. So we've talked about this some already. So it's a bunch of interrelated decisions. So we have to choose the length of our wires. So for example, and we usually use the parameter L to represent that. So in this architecture, if you look at it closely, you'll find that all the wires are length 3. I think they're all length 3. Let me look at them carefully. Yeah. So they go past 3 logic blocks and then end. We have to decide how many programmable switches we should put in. We have to decide what the pattern of switches are. And we often divide that into 2 pieces. What is the pattern between wires? And what's the pattern to from blocks? And then we have to decide how we're going to electrically build this. So our kind of simplest and smallest configurable switch in a standard manufacturing process is just an SRAM cell controlling a pass transistor. And we saw, well, we could change that into a transmission gate. That's a little more expensive. We can also build things like this, where we actually build a buffer. So these 2 inverters back to back are a buffer. First one's small, second one's big to drive a bunch of capacitance. And then build big pass gates after that. So we can basically integrate buffering into the routing too. And there are a few other ways we can design the switches electrically beyond this. So that's another choice we have to make. So we usually, in the end, the CAD tools don't really care about anything except where are the wires and where are the switches. But we often divide the switch patterns into pieces just to make it easier to think about. So one piece is what we call the output connection block, which is taking the outputs from the logic blocks and other function blocks and connecting them to the routing wires. The input connection block that does the opposite, from the routing wires to the logic block inputs, and the switch block, which connects routing wires to each other. Let's see. Okay, so connection block, one of the questions is how flexible do we need to make this interface between the outputs and inputs of a logic block and the wires. And people have named that FC. So FC is the standard variable we use to talk about how many wires in a channel that's going past some input pin or output pin on a block can we connect to, okay? So it's called the connection block flexibility. We often use different values for outputs and inputs because the electrical cost of building those things is different. So let's just see if you understand this notation. In this little example, what is FC input? Alex, what do you think?
The connectivity of the input connection.
I just want a number. On this example, what's the FC input? This is, yeah, okay, so it's 3. Okay, so Alex is with me. What's the FC output? See if anyone else can get this. Who said? You said 2? No one said 2? 2, you're right. Okay, good. So you're with me. So yeah, just how many switches? We also often normalize them to channel width, right? So FC input is both, it's 3, or we could say it's W, because it's every wire in the channel. And FC output is 2, or we could say it's 2/3 of the channel width, because 2/3 of the wires can connect to it. Okay, how do we build these? Okay, let's look at this input connection block. How would you build that electrically? So I've just drawn these X's between the wire and the input block, but I can't just build X's on my chip. What should I build to make this happen? Yeah, so this is a mux, right? It's a select function. I need an FC input to 1 mux. So yeah, I've got these routing wires. I build a mux, some SRAM cells to choose which one goes through into my input pin. Okay. The output connection block, well, can we build it as a mux? It's basically backwards. You can't build it as a mux. It's actually, so I can't build it that way, or at least not the same kind of mux. So different ways I can build it. I could build tri-state buffers. So I could say, okay, I can drive this wire, or I can drive this wire. I could build a separate tri-state buffer for each one of those X's. Okay, so what does that mean? Here's my output pin. That's this node. And I've got an SRAM cell, which if I put a 0 in, it basically disables this. It's going to turn off this transistor and this transistor no matter what. If I put a 1 in, then basically let's see what happens if I put a 1 in here. Okay, If, if I put a 1 in, basically, that logic just goes away, effectively, and I'm just connected to an inverter. Okay, so that's my tri-state buffer, and because you lose a lot of IQ points when you're trying to do something on a slide, I'm not going to like just work out all the logic, but trust me, it is correct. So I could do that. Another way I could do this is I could build one buffer. So maybe that's a couple of inverters. Usually you build a little inverter, then a big inverter, and then I could put pass gates after it, each of them controlled by an SRAM cell. And each of those outputs of the pass gate would connect to a different routing wire. This is basically another way to build a tri-state buffer, okay? So both of these are like valid ways to build it. And depending on your transistor sizing and electrical properties, you know, one or the other of these might be more efficient. Is everybody with me? Does it make sense? Okay, so connection block flexibility. So it's a classic trade-off. If I make FC higher, what's bad? Okay? So Alex, what's bad? Yeah, so my muxes get bigger or I get more tri-state buffers, so it's expensive. What's good? I said it's a trade-off, so there must be something that's good. Yeah. Yeah, it's easier for my router. I've got more options. More wires can get into my input block, my inputs, my output can drive more wires. So it's very hard to say what the best value is, right? So yeah, as I make more switches, obviously things get larger. It also has some speed impact because as I make my muxes bigger, they get somewhat slower. As I make more tri-state buffers, I load my wires more, so they get a bit slower too. But what's good is that I can use a lower channel width because there's less blocking. So I can use a higher fraction of my wires before I run out of options. So that saves me some area. And also if I save area by making my channel smaller, all my wires effectively get shorter, which cuts their capacitance, cuts their resistance, so that actually gives me some speed too. So it's a complex trade-off space. You can't really just differentiate this and say what's best. Okay, so it's a trade-off, and people study it empirically with CAD tools. That's what you will do an assignment for. Okay, we kind of talked about this earlier. This is basically an earlier version of the VTR flow, and it was used to look at what is the best connection block flexibility. And what they found is that it basically depends on exactly what happens inside your cluster. So it's not the same for every kind of cluster. So if we use these logic clusters, they have n of these, you know, LUTs or fracturable LUTs inside them, and we have a pretty flexible local interconnect. Okay, so that's what was assumed in this particular study. Then if we just have one logic element, then choosing FC to be pretty close to the channel width is a good choice. Okay, your channel's not that wide because you don't have that many inputs or outputs, and there's no more switching once you get inside the logic block. There's no local interconnect, so making pretty much all of the inputs and outputs able to drive into it is good. As you make the logic block bigger and you have this crossbar local interconnect, this particular study found essentially you can drop, as n gets bigger, you can make your FC input and your FC output smaller, okay? Because if you look at this number, n is in the denominator. So it says the more things in your logic block, the smaller you can make FC input. So why do you think that is? Or at least the smaller in terms of fraction of the channel. Does this make sense or not? Isidore, why does it make sense? It does make sense, I think. So I'm with you. I'm agreeing it makes sense. It's not a bait and switch. I'm not saying why does this make sense, but I'm secretly thinking there's no way this makes sense. It does make sense. So it's due to this crossbar local interconnect, right? Is that a hint? What is happening as I make my logic block bigger and I have all this local interconnect? Yeah, essentially, if I have a flexible local interconnect like this, so say I have a full crossbar local input, local interconnect, then what the FPGA router has to do is it doesn't have to get to a specific input pin of the cluster. It just has to get to any input pin. And then the local interconnect will get it to whatever LUT or flip-flop it needs to get to. That's an easier routing problem. Okay, so by being able to reach any one of the larger number of inputs that exists on these larger logic blocks, we saw in the Rose and Ahmed paper, this is how many inputs they recommend you put on these blocks, and it gets bigger as the logic block gets bigger. So this is a bit of math, but it basically says, because I can reach any one input and still get to where I need to go to, I can essentially cut what fraction of wires can reach a specific input. And I still have the combination of the input connection block mux plus the local interconnect still gives me enough flexibility. That's what this is doing mathematically. It's a similar analysis for the outputs. If the outputs can also be swapped around, which they can in Intel-like architectures, you similarly come up with, as the logic block gets bigger, you can cut this FC input and FC output and only kind of be able to access a fraction of the wires, and you rely on the local interconnect to make up for it, because you can just get in and out using any input or output. Does that make sense? So this is a function of exactly how you design your local interconnect. If you didn't have local interconnect, you probably wouldn't be able to do this so easily. So it's one of the things it's doing for you. Okay, so that was the connection block. What about the switch block? So, so for switch blocks, we use the term FC to mean how many wires an input or output pin can connect to. For the switch block, we use FS, number of wires that we connect to at some switch point. So this was originally done for just length 1 wire. So say at the end of a wire, the wire ends, how many other wires can I connect to? How many switches do I have? Okay, so in this example, so here's a wire, this one, it ends, and this is what I've got. I've got 2 switches hanging off of it, so what is FS? It's like super obvious, right? It's 2. Okay, so this example is 2. Now, if I show all the switches, I have to put in all the switches for every wire that's ending, so I get this pattern. Okay? So FS is 2. So that was the easy question. What do you think? Is this a good switch block? Usually I have to use a CAD tool to evaluate that, right? But do you think you can evaluate this graphically and tell me if it's a good switch block or not? What do you think? Yeah, do you like it? So Hale, what do you think? I can tell you're thinking about it. Right, so at the end of this wire, I can go straight, keep going. Seems useful. Maybe I'm trying to get halfway across the chip. I also can go up. Seems useful. Maybe I need to go to the top right corner. I better not want to go to the bottom right corner, because I actually have no switch that goes that way. Okay? So this would be like if you made a city where you can go straight through intersections and you can make left turns, but all right turns are illegal. I think actually my neighborhood is approaching that, but it would make it very difficult to get around. So yeah, this FS is not a good idea. So FS less than 3 is usually a bad idea. So yeah.
Go into the logic block and then go out a different exit from the logic block.
Yeah, you could do that. And so you could do what's called the route through. Yeah, go into the logic block, come back out. But you're kind of chewing up some of the local routing just to go in and out. So what's the equivalent of that in the city? You have no right turns. However, you do have parking lots. And you could go into somebody's parking lot and sort of drive through their drive-through window, say you don't really want a burger, you're just trying to make a right turn. and maybe it would be better than nothing, but probably not the world's best city plan. So yeah, so some switch patterns you can actually look at and just say that doesn't seem like a good idea. This one is not a good idea because it clearly doesn't have enough flexibility. Okay, so there are a bunch of papers that evaluated what are good switch patterns for length 1 wires. They're mostly just done on length 1 wires. And for length 1 wires, the best value of FS was found to be 3. Because that's enough. You can go straight, turn left, turn right. If you have fewer switches, you have the problem that we just saw. You can't go in all directions, which is pretty bad. More switches is not necessarily bad, but in most of those studies, they found that it wasn't necessary. So basically, if I have a higher FS than 3, so 3 is pretty important. After that, I might just say, well, now I can go to this wire too. That's 4. Maybe I can go to that wire. It's 5. It's easier to get around blockages. So there's some benefit to it, but I also added a bunch of area. So early studies on this said FS equals 3 is probably the best. Higher values are okay. Lower values are not okay. Longer wires are actually less studied. So there are a few papers that have looked at this, but not as many. But they indicate that FS, at least 3, maybe higher, makes sense for these. Metal area is getting more important. Like it's easy to run out of metal. Probably pushes you towards somewhat higher FS values because you don't want to waste, especially a long routing wire. There's maybe a little more pressure to, let's make sure it doesn't get blocked because maybe and maybe I'm not limited by transistor area so much, so throwing a few more switches in is not so bad. Yeah.
It's a classic architecture question. Is there a reason why you would always be the same FS for every switch block, and is the reason just because
It actually doesn't have to be. So I mean, as we get into more complicated chips, FS kind of gives you an idea. And for the early architectures that actually only had one length of wire, it was kind of precisely defined. As we've gotten into more complicated architectures with different wire lengths, essentially some of them usually have more switches than others. So you don't actually have kind of just one FS for most modern architectures. It'll vary a bit depending on the wire type. Does that make sense? Okay, so now we're going to build the switch block. So electrically. So I already showed you both of these. I could build a pass transistor controlled by SRAM. I could build a chain of inverters and then put big pass transistors on its output. So either of those is possible. The nice thing about pass transistors is they're bidirectional. So if I make one pass transistor, it's actually going to allow me to go, from here to here, or it's going to allow me to go from there to there. So if that makes sense to you, right? So no matter which way my router is trying to go, from left and up, or it started out up and it's going down into the left, the pass transistor, one switch can make that connection because it's bidirectional. If I build this kind of structure, which is a form of tri-state buffer, I have to build 2 of those basically if I want to be able to go both directions. So that's going to increase how much area that takes to make a switch that goes both ways, like I have here. Does that make sense? Okay, so we're going to talk a bit more about that there's one of those papers that I talked about on directional wiring that goes into that more. Another thing that you need to think about is the topology of the switches. So not just how many switches you have, but like what's the pattern. And let's see. Okay, so one of the, whoops, I think I've got an automatic switch on this. I'll have to go fix this afterwards. Let's do that. Okay, so one of the earliest switch box patterns was called the planar or disjoint switch block. And essentially, you could number all the wires. Like this would be index 0, index 1, index 2. So you had essentially planes. All the wires in index 0 that I've shown here can only connect to other index 0 wires. All the wires in index 1 can only connect to index 1 wires, and so on. Now, benefit of this is that it's easy to lay out. So it's very regular. It might, depending on how you lay it out, you might be able to do it with somewhat less metal in your muxes, which is a big benefit and actually becoming a bigger benefit all the time. So that's a good thing about it. What do you think? Is there anything bad about it? Yeah.
without driving to purchasing, you're not going to be able to ever go from like 0 to 1 ever. So if you have like 4 very high fan-out nets, they would all be conflicting, or at least one of them can be conflicting with one of the plans.
Yeah, it's hard. So that's a good point. So basically, it's easier for this to get blocked. So various studies have shown that you need a higher channel width when you use this kind of switch block because it's easier to get blockage. And hopefully it's going to animate anyway. So, whoa, Interesting. Okay, I must have something I need to fix in the slides afterwards. It's like basically does not want me to spend long on these slides. Um, yeah, so the planar switch block, essentially no matter what I do, if I come out of a logic block, go into track 0, whether I turn left on this channel and turn right later or whatever I do, see if I can actually draw on this without it changing things. This is looking promising. Okay, so if I come out of a logic block, and let's say I go into track 0, and I keep going and to another wire, that will also be track 0, and then I turn vertically, go into a wire, that's also going to be track 0, and so on, and maybe eventually come here, and that's where I wanted to get to. I'm going to be on track 0 all the way, no matter, as soon as I started on track 0. If the router detoured, and basically said, well, maybe I'll go down here and over here, and then I'll come up here, it's still going to be on track 0 when it gets there. Okay? It can never, the only way it can get to track 1 is at the very start. At the very start, if it was able to connect to a track 1, if it had enough FC options and one of them was open, it could get me onto track 1 and actually get to different wires at the very end here. But that's the only way you can do it. So that increases your probability of routing blockage. So this is sorry, that's really annoying. This is the Wilton switch block. And it's almost the same as the planar one. The only thing it did is going straight across still goes to track 0, going up goes to track 0, but going down kind of goes to track 2. It goes to as far away in track number as it could. So it just rotates it over by 1, basically. So it's not that hard to lay out either, because that's not that different. It just does this rotation. It has the same number of switches, but what it does is, see if I can draw on this. Now, if I come out and I go and start on track 0, if I go this way, do the same thing I just did, I'll wind up on a certain track at the end here. I guess the way I drew this, I would wind up on track 0, because all of those turns that I did don't change the track number. But if I came out and then I went down 1, I basically detoured a bit, I switch when I go down 1. So now when I come across here, I'd wind up on track 2. Okay, so by taking a different routing path, I'm able to get onto a different track at various points along the route. So it's basically harder for this to get blocked. Okay, so I guess the basic principle this illustrates is if you can scramble your pattern some, like very regular patterns are a little bit dangerous. If you scramble the pattern a bit, you actually are giving more options to the router. It makes a different decision at a certain point, and it gets into a different set of wires. And you'd actually like to maximize that. The thing you have to watch for is what the first very dense paper was talking about of last week's reading, is essentially layout effects. You would like to make your pattern irregular, but you still want to think about how these are going to be built in muxes. You don't want your muxes to be connecting to wires, or your switches connecting wires that are far apart and dragging lots of metal around. So there's kind of two contradictory things. You'd like your pattern to be quite regular and only connect wires that essentially cross each other or come very close. But you'd also like your pattern to do some scrambling of which wires you can connect to. Yeah?
So what's probably logically equivalent, instead of handling this in the switch block, do you not instead say in the trunk, where you just have like a bunch of wires going side by side, that at some point those apply, like in the metal, they apply rotation, where you're just going to basically physically move these 3 wires.
Like for longer wires?
Yeah, along the long twist it as you go through.
It's possible. I guess the thing that this one does is depending on which decisions the router makes. Like if I'm going on a diagonal, if it decides to turn twice versus once and so on, it's going to get onto different wires. And so that's kind of giving it more path diversity. I'm not sure you would get that just by along one longer wire having a fixed pattern of how you switched. Okay. All right, that was switch pattern. So this is kind of a quick intro to a bunch of different questions. Sure. Let me just hide this again. Yeah.
How come on the please flow diagram?
The diagram that won't stay up.
Wouldn't it make more sense for when in the pass-through case where you're going straight,
Yeah.
instead of connecting 0 to 0, connecting like 0 to 1, 1 to 2, 2 to 0, and then that way, as you're going straight, if you know you're going to need to turn at some point, choose which like type, because if you're going to assume that like wire 0, 1, and 2 will connect in some regular way to the labs, like
Yeah.
wire 0 always connects to the top in this particular path bin or something, you can choose which one you want to get, but effectively by like deciding when you want to turn.
It's probably, I'm guessing it's isomorphic, like that also would work. I think the key is to have some of these rotations or scrambling. The Wilton switch box shows you don't need it in every direction. If you did it in one, it was fine. I can't prove this, but I think if you just move the rotation to be the straight through path, that it would probably work fine too. But that's what I think, but I don't know for sure. Okay. Okay, so wire lengths. Okay, so another question we have is like how long to make the wires. So this picture is just to illustrate the trade-off. So let's say I make all my wires length 8. So they're good for this case, right? I want to go 8 units. So I do that just by turning on a programmable switch at the start, turning on a programmable switch at the end. In between, it's all metal wire. It's about as good as I'm going to get. So that's great, but it's wasteful for this case, right? I need to go just between these two blocks. They're only 1 unit apart. I still have to turn on this programmable switch, turn on this programmable switch. I've basically wasted a lot of metal area because I don't really need this long wire, but I've laid it out. It's costing me area. It's also got extra capacitance, which is slowing me down, costing power. So that's the trade-off of the good and the bad of a longer wire. If I was to make length 4 wires, basically this long connection is probably going to be worse. Okay, it's got the same amount of metal, but it's now got a new programmable switch in the middle. So that programmable switch is going to add some area. It's going to add some delay. So I'm a little bit worse for the long connections. But for short connections, this one has got less extra capacitance, so it's actually faster. And now in the same layout area, I can make another wire, and I can make this other connection. So clearly I can get better routability with short wires too. Yeah?
And I'm under the impression, and maybe I'm missing something here, that length 4 wire, you can't exit it at length 1. You have to exit it at length 4, and if you want to go length 1, get on a length 1 wire.
So it depends on the detailed architecture you've got. So historically, most architectures, once you got on a length 4 wire, you could get off at any point. Okay, but it's something you can control. So you can actually play with that in assignment 4, for example. Assignment 4 is the last one. So you can actually control that in the VTR CAD system. When I get on a length 4 wire, can I get off at every point or just at the very end?
Wouldn't it be prohibitive for like if you have a length 16 wire, for instance, like the long wires?
Yeah.
The parasitic capacitance of having 15 other exit points connected to it could really grow.
Yeah, so it gets more common with long wires. So we'll talk about that in a minute, but you're right. There is a cost to being able to get off of this every point. Via stack, you have some programmable switches which have capacitance hanging off of it. So there is a cost to having the ability to get off at every single point. For most architectures, until you got to quite long wires, it was typical to be able to get off at most or all of these points. In the latest architectures like Agilex, because the via stacks are getting very expensive, it's more common not to get off in the middle. So yeah, there's a lot of detail there, and there's some change going on. It's getting more expensive to get access to these wires. So even the shorter wires, you're often not able to get off in the middle anymore. But in most architectures over time, you could get off in the middle. And you can still build it. It's just whether you want to build it or not.
The other piece about that, like the follow-up to this,
Yeah.
would be that you would need to add all these muxes now. The number of ports that you would have in your switch pattern that you're receiving to drive and show off would be a lot larger if every single wire, or conversely, you could have more wires with the same number of ports.
Yes. Yeah, you're right. So there's a very complicated trade-off space there. So usually these wires are also, so these wires are drawn thicker because they're usually higher up in the metal stack, especially if they're relatively long, so they're kind of more expensive. So the cost function is pretty complicated here. The via stack takes some area. That wire, especially if it's high up in the metal stack, you can't build that many wires that high up in the metal stack, but those are the ones with lower resistance that you like. So you kind of prefer not to waste it too. So you got a lot of competing goals. But you're right, there has been a trend to reduce the number of points at which you can get off a wire.
Yes. So I guess in the earlier readings for a particular Intel architecture, there was no exit point for longer length wires. Like for example, if I want to go from length 8 wire to a logic block, I need to go via some length 4 wire.
Yeah.
Exit to a length 4. So
Yeah.
I don't need those many exit points.
Yeah, that's true. And I'm going to show that in another couple minutes, actually. So it's another routing architecture trick. So you guys you're on your game. It's great. But the basic trade-off that you want to understand before, these are all good points. The very basic one is, yeah, short wires are good for short connections. Long wires are good for long connections because each one kind of suits the purpose well. So we usually wind up with a mix of them. So this is a paper they were signed a couple weeks ago, and it said, okay, if I just have one wire segment length, that's what this plot is showing. So I make all the wires the same length so I can understand the architecture. What do I get across a suite of benchmark circuits in terms of area delay and then routing delay? So if we look at just delay, basically length 1 wires result in more programmable switches than you'd like. Okay, most connections are more than one logic block away, and now to make those connections, I have to go through multiple programmable switches, which adds some delay. So it's not as fast. If I make all my wires length 2, it's faster. If I make them length 4, a little faster still. If I make them length 8, slower again. So length 8, that's actually beyond, with a fairly good placement engine, usually I told you that you can get an average distance of how far you go between output to input of about 4 units. So length 8's a bit too long. So now it's pretty good for longer connections, but shorter connections are just taking a bunch of extra capacitance. And it's actually costing us speed. When we look at transistor area, so this is not metal area, but transistor area, which historically dominated FPGA area, but increasingly you have to think about metal area too. It's a similar picture. Okay, well, it's actually area times delay. So this is the combination. So when we factor in area and delay, length 1 looks bad. Length 2 looks pretty good. Length 4 slightly better, but not much. And length 8 is, again, worse. So we wind up with a broad minimum. 2 and 4 are pretty good. So we don't want to make a routing architecture with only one kind of wire, but this gives some idea of that's probably our workhorse, right? Like maybe we make some shorter, some longer than that, but we should probably have some wires around that length, like a lot of them around that length. Yeah? No, there's no particular reason you have to do that. It's just too many data points, takes too long, and makes a cluttered graph. So that's why. Maybe. Okay, so length 4 was the best here. Their earlier studies and older technologies showed length 4 was significantly better than length 2. Okay, now it's still a little better in 22 nanometers, but not much. Why do you think it's gotten closer? And length 8 used to be not as good as length 4, but it wasn't that much worse. Now it's actually quite a bit worse. So what do you think? This was done at 22 nanometers. Some of the studies that said length 4 was significantly better than 2 and 8. Significantly better than 2 were in older technologies. So what do you think has changed? The technology has changed, but why? Why would they push you that way? What do you think?
The relative cost of having the longer wires using buffers faster, those kind of technologies.
Yeah, you're more and more dominated by, it's been for a long time, wire capacitance was the most important thing. So those older studies, wire capacitance mattered a lot too, but wire resistance has gotten more important. And wire resistance makes longer wires less desirable because basically putting a programmable switch in, if it's got a buffer in it, it actually stops the accumulation of resistance. So yeah, it has a cost in delay and a cost in area, but also as a benefit. It stops you from continuing to accumulate resistance in your signal path. So even in an ASIC where they don't have to put any switches in, they won't run a wire more than a certain distance, like certainly not from one side of the chip to the other. They'll start putting buffers in. So those trends push FPGAs towards somewhat shorter wires. Does that make sense? Yeah, the paper that I think only 2 people read, but I said is a really interesting paper on global is the new local. Basically, what the author is arguing is even logic clusters in 3 nanometers, the wires are too big, right? So even that local interconnect has to be now broken down into essentially multiple levels of hierarchy, or we need to use smaller logic blocks, et cetera. That all the wires are getting so resistive that you need to make a lot of very short wires, at least in the low levels of the metal stack. As you get higher in the metal stack, you can make wider, thicker wires that are lower resistance, but you can't make as many of them. So that's a big challenge. So that's my pitch for reading that paper. So let's see. Yeah, and this is just a picture of like what do these metal stacks look like. I guess that's illustrating. Down here, you've got lots of wires, but they're very small pitch. They're not very thick. They're quite resistive. Up here, you've got much thicker, wider metal. It's not as resistive. You can go a lot farther, but you just don't have nearly as many of them. So for your common wires, it pushes you to make them relatively short. Let's see what is going on with this. Okay, let's see if I can move on to the next slide. Okay, switch box electrical design. So, and this is also actually, this is strange. The various computers are shutting off on me up here. So, okay, routing. How do we design the routing switches? So, okay, we talked about pass transistors. We talked about a couple different ways to build tri-state buffers. And there's another kind of switch you can build that in the literature is called a direct drive switch. And it looks a lot like this, right? So this is a buffer. It's typically built with 2 inverters, a small one and then a big one, so it can drive more capacitance. And because there is a fair amount of capacitance on a routing wire, it's pretty big. This direct drive switch is kind of just the opposite, right? We put pass transistors on the input, and then we have, that's weird. Okay. Sam Altman's back at OpenAI, and it looks like the AI has become self-aware already. It's possibly taking over the lecture. So, it's a concern. Okay, so this direct drive switch kind of looks like just the opposite of the tri-state buffer switch. But those are kind of our menu, our 4 kinds of ways we can build switches. 2 different ways of tri-state, direct drive, pass transistor. So let's see what's going to happen when I click on this. Yes. Okay. So what do you think of these? I guess pass transistor. It's small, okay, and it's bidirectional. You can go either way. Those are both good. What's bad about a pass transistor? It sounds great. I mean, what's not to love? What do you think?
As you start to go through it, right, the capacitance and whatever gets worse.
Yeah. So it basically, let's see if I can draw this on here. So if I take a bunch of pass transistors and combine them. Yeah, so there's a voltage drop. So I could get rid of that voltage drop if it really bugs me by using a transmission gate. It's hard to use a level restorer in this case, but I could use, because I'd like it to be bidirectional, so it makes it harder to do. So mostly if I got worried about it, I'd probably use a transmission gate. So, but let's say I've got my output of my logic block here. So I've got a buffer. It's a tri-state buffer. Let's just draw it as a buffer. And then I put my pass gate here. Another pass gate here, and so on. Another pass gate here, and maybe this is where I go into a block. So I have 3 pass gates in series. So none of these basically drain to ground. Okay, like there's no buffer in this. So the resistance along this wire and through these switches just accumulates. You can approximate the delay of a circuit like this by what's called the Elmore delay. People know what the Elmore delay is? Is it because I talked about it in this class, or you just knew about it already? How many people don't know what the Elmore delay is? Okay, so Elmore delay is it's essentially the first time constant of a circuit. Okay, so if you remember a resistance and a resistor capacitor circuit, if I just take this R, C, and I work, I can write the differential equations for charging and discharging that, and it'll be an exponential. And the time constant of that exponential, so this V out here, would be equal to e to the negative t over RC, okay, for discharging, okay? So the time constant is R times C, and that just comes out of the differential equation. If you work out this circuit that I've drawn down here, the pass transistors are nonlinear, but we ignore that. Let's say we say, okay, let's model them as linear resistors, which you can do with some error. Okay, so it's more accurate to model it in SPICE. But if you take what is their resistance in the middle of their operating range, it's not a bad approximation. All these wires have capacitance. Okay, so there's a capacitance here, there's a capacitance here, there's a capacitance here, here, etc. You can work out the time constant of this circuit. And the first time, it actually has more than one exponential, okay, so it's a more complicated one. But the first time constant, the most important one, is what's called the Elmore delay. The Elmore delay is you take every capacitance, you multiply it by the total resistance to ground, and then you add that up for every single capacitance, okay? And that will give you the first time constant of this circuit. So I've approximated things now in two ways. I made my nonlinear resistors into linear ones, and then I approximated the delay of this by essentially the first time constant. But if I do that, I get this capacitance times 1, 2, 3 pass transistor resistances. This capacitance times 1, 2. This capacitance times 1. And let's assume this buffer is really powerful, so we'll ignore that one. If I add one more routing switch, I will take the capacitance of that routing wire times 4 pass transistor resistances. If I add another one, I'll take the capacitance of that times 5 pass transistor resistances. If I sum that up, because the delay is I add all of that up, the capacitance times the resistance of its path to ground, it's growing quadratically, okay? So add one more segment, it's a quadratic growth. So pass transistors can be fast as long as you don't hook too many of them in series. But if you have to go all the way across the chip and you hook a whole bunch of them in series, the delay is catastrophically bad, okay? So you can use some pass transistors, but you can't use all pass transistors because their delay scales really poorly if you start cascading a bunch of them together. Okay, so let's see if I have that on the next slide. Maybe I do, but let's just, what do you think about this one? So what do you like and not like about this? Compared to a pass transistor. Yeah. You like that one, okay? So you don't like this one that much. Anyone like this one? You like it. What do you think?
It just has like a buffer which kind of like divides the load, so you don't like experience that like almost delay on the load that you
Yeah.
get in a pass transistor.
So the delay of this will grow. If I connect like n things in series, like n routing wires driven by these switches, it will grow linearly. Okay, so it's got much better behavior if I have to go all the way across the chip. Cost, what did I pay for that though? I paid something. Actually paid a couple things. Yeah, it takes more area. This is bigger. For a given amount of sort of drive strength, this is always bigger. The other thing is it's not bidirectional. So if I want to go both ways through a switch, I actually have to build two of these back to back. This is kind of just a different electrical trade-off. It's got more gates in it, but the signal path driving a big load here has 2 transistors in series, and the signal path here is 1. So it depends. If you're driving a really big load, this is actually probably better. If you're driving smaller loads, this might be more area efficient. Okay, then what about this one? What do you think? So Isidore likes that one. Is that an irrational love for just putting the pass transistors on the left because that's what happened back when he was in elementary school? So.
I'm team pass transistor.
Okay, so you're on pass. Isidore, why do you like this one?
I like this one because I've seen it.
Was it in elementary school? Was that right? Your elementary school was that advanced?
I also like though that if there's any like, you know, in terms of the capacitance, like you know that after that, you know, anything you're gonna drive after this is actually stored.
Yeah, so it's similar to this one, but the reason this one is actually really nice, so the nice thing about this is we haven't drawn the routing wires, but the routing wires are big. They're relatively long, they're high capacitance. So this can be made big. Usually a couple of buffers and inverters in series, the last one quite significant, to drive that big capacitance. These can be kept close to this inverter or this buffer. So these have small capacitance. I can make these small, okay? So these one on this side, these are connected to the big routing wires. I can't make these small. I have to make them big. Does that make sense? So it looks very much like it's a mirror image of each other, but when you think about the loads, I can make these a lot smaller. Does that make sense? Yeah. You basically can't. You have to turn on multiple direct drive switches. So if you had a lot of, you're right, that this gets to share the buffer across multiple connections, so that's maybe an advantage there. If I had a lot of cases where I want to connect this to multiple things, that actually might be more efficient. The other thing is I can actually, this buffer, I can tri-state this. So this routing wire, I can turn this off, and it's totally isolated from that. This cannot be turned off. Okay, I didn't put a tri-state on this. So if I have no tri-state on this, this is the only thing that can drive that whole routing wire, okay, which seems like a pretty significant limitation. So electrically, this is quite nice, but it has a pretty severe limitation of I can't shut it off. So this wire is going to be unusable unless I wanted to connect one of these things to it. Does that make sense? Okay, so actually I showed this. This is all the same thing that I just showed you. We just talked about this. Okay, so we already talked about this, so good. Yeah, and you can mix tri-state buffers and pass transistors, and it can work pretty well, but you need at least some buffers or tri-state buffers in your architecture. And yeah, I just talked about this. So yeah, electrically really nice. Getting rid of the tri-state, doing all the switching on this low capacitance node is good. But we've got this big limitation on our switch pattern of I can't shut this thing off. Only one drive point per wire. Yeah. It's not hard to model in the CAD. So the actual routing CAD tool takes it takes a graph representation of the wires and switches. So the wires turn into nodes, and the input and output pins turn into nodes, and the switches turn into edges. And normally you do directed edges. So you can represent this pretty directly. If it resulted, I guess, in circuitous routes, that could make the CAD tool slower. But it would have to result in sort of circuitous routes because it's not any harder to represent. It fits into the graph representation very well. Does that make sense? So I'm going to go a couple minutes over. Let's see if I can quickly go through this paper. Okay, so this is one of the papers you were to read. I can go over it here, and then I actually extended the due date, so super easy to write the, don't tell anybody who's not here, super easy to write the summary. So if there's somebody really clever, you could ask a question in the middle, like going, hey, what do you think about this? Okay, so this work was done in academia, and actually at the exact same time we were looking at this inside Altera. So it's a case where it was both commercial and academic work happening at the same time. So Guy Lemieux is the first author of this paper. He's now at UBC. And basically he looked at, okay, let's say I'm going to make tri-state buffers. So give up on pass transistors, they don't go all the way across the chip. I make tri-state buffers and I still use a bidirectional pattern, meaning all my switches can go both ways. I actually have to build back-to-back tri-state buffers for all my switches in the routing. And I can guarantee I'll never use more than half the switches because it's just fundamental, right? I'm either going from right to left or left to right on each of these points. I'll never use more than half my switches. So we thought that was kind of frustrating. If he looks at that for an entire switch block, he basically went, well, if I pick the direction in advance, like this wire can only go to the right and this wire can only go to the left, he basically found, well, I have to kind of think about pairs of wires now because I need to have one left-going wire and one route-going wire as kind of a pair, otherwise this doesn't really make any sense. But if I think of it that way, I basically can remove an awful lot of switches. So this is just showing what muxing and tri-stating I would need with the typical bidirectional switch pattern versus if I choose directions in advance. And it basically is able to get rid of the tri-states because you say, I'm going to only drive from one spot, and you can get rid of a lot of the muxing. In the classic bidirectional routing, I basically don't know where I'm driving a wire from. So if I look at this wire here, let's see, yeah, this wire, I might be driving it from using this buffer. There's another buffer way out here. I might be driving it from that. So I got to be able to tri-state this. And I also might be driving it from a logic block. So I put a big pass transistor on there. Essentially another way of making a tri-state. There's a buffer and then there's pass transistor. So my outputs from my logic blocks, I have to be able to tri-state them so they can either turn on or off with this kind of architecture. And he calls that multi-driver routing. Once you decide that there's a direction to a wire, okay, so now that same wire that I was showing you, he's basically decided that wire is going to go to the right, okay, at architecture time. So he only builds a mux, like a direct drive switch, and he keeps the tri-state, so the buffer still can be tri-stated, but now he knows this wire can only go to the right. There is no switch out here that can drive it. And he can still use a pass transistor to connect it to the output of a logic block, and this works fine. Okay, so you can still use tri-states if you want with this directional routing architecture. But you can also go one step further, where you say, okay, I'm only going to have this logic block connect to wires that have an endpoint very close to me. If it has an endpoint very close to me, I can go into its mux. Okay, so I'm not going to drive it with a tri-state driver. I'm going to drive into the one mux that's already there. And now I can actually take off this tri-state. So there's no longer a tri-state on there because all of the signal drivers for this have been brought into the mux. There's no reason to be able to tri-state this anymore. And he calls that single driver routing. Does that make sense? Yeah.
So now I was reading this, I'm a little confused. Doesn't this destroy the whole concept of connection block?
Your connection block electrically has to be coupled with your switch block in this architecture. So you can still think of it topologically as how many wires do I connect to, but you're right that you can no longer point at a spot on the chip and say that's my output connection block. Your input muxes still exist, but your output one has been merged in electrically into the switch block. Yeah?
If you were to do this, then wouldn't this also kind of lend itself to the early exits and having things come out every point? Instead, it's basically saying like, okay, all the wires that end here, we'll replace sort of the cuts, and then everything that ends here, we're going to bring in a new driver for. So you basically pair the beginning and the end of the wires.
I'm not sure. I might need you to draw that for me afterwards. So, okay, but we've got a major connectivity constraint. We can only drive the wire at one point. Like once we took this tri-state off, we just cannot drive this wire any other point. So every single thing that's going to be a possible driver for it has to come from the same general area. So the question is, well, how bad is that constraint? And it surprisingly turns out to be not that bad. So this is an area over a bunch of benchmark circuits. And the most interesting thing is probably this one, the geometric average. Okay, and he's got two bars here. So the cross-hatched one is he's made the architecture directional. So every wire, goes one way or the other, and he removes all the switches that don't fit that. And it actually saves a fair amount of area, maybe 10% area. And when he makes it not tri-statable, it saves even more area. Okay, so so what that means is the CAD tool didn't have to increase the channel width very much. You think maybe this connectivity restriction is really bad, it'll need a lot more wires. It didn't need that many wires, more wires, it needed a few. And the increase in the electrical efficiency, like the layout efficiency of this, meant it was a significant area savings. Okay, what about delay? Okay, so the directional with tri-states actually on average, this is the geo mean, did actually slow the circuits down some. Okay, so making the architecture directional, there was some more detouring because the switch pattern is more limited. That cost 5% speed or so. But once he took out the tri-states, that is so much better electrically that even though it makes an even stronger connectivity or switch pattern constraint, he's now about 10% faster. Okay, so if you put it together, you get the area delay product. And whoops, let's see if I can get out of this. Okay, okay, so you get the area delay product. Here's the geo mean. basically, the directional tri-state saves maybe 15% area delay product, and if you take away the tri-states, it's getting almost 30%, which is actually enormous, okay? So when you make one, this is a big change, your whole electrical design and your connectivity patterns change, but this is like a gigantic improvement in efficiency. So, yeah, so it worked very well. I think I'll leave off for there today. I'll briefly go through this paper, which is on Stratix. So Stratix was the first Altera architecture to use direct drive. So we basically had academia was looking at this the same time we're looking at it in Altera and switched entirely to direct drive. So this is an academic result that definitely proved to be agreed with by industry. Okay, so we'll leave it there for today. Sorry for going a few minutes over, and we'll pick up on routing architecture next week.